Okay. So let's start our afternoon session. It's a pleasure for me to introduce Diego Noja. And the title of his talk is the NLS equation with isolated singularities. Please. Thank you so much.
No, ti regoli con quelli che ti vedono a casa, capito?
Ah, ok. Vabbè. No, perché?
Non ti vedo.
È sicuro di diventare
Esatto. Poi ti giri. Togli forse quell'effetto di...
Vabbè. Ok. Perché no?
First place, thank you so much to the organizers for having invited me to the meeting.
Il microfono alla bocca.
Thank you. Many thanks to the organizer for inviting me to the workshop and for giving me the opportunity after 1 year and a half to meet all of you, friends and colleagues in person. Let's hope that we can come back to the normality as soon as possible. Okay, my talk is about the nonlinear Schrödinger equation with isolated singularities, and more precisely, is the plan of the talk. I will begin with the main subject, which is the nonlinear Schrödinger equation with the point interaction. Then I will explain why I speak of isolated singularities. And this is the next point. A small review of a completely different subject from a different field in analysis, isolated singularities in nonlinear elliptic equations. Then I will give some preliminaries on point interactions and a statement of the main result of the work, and finally a sketch of the proof according to the time. Okay, now let's begin with the main subject. We want to discuss the well-positiveness of an abstract nonlinear Schrödinger equation, which is given in the boxed line. A nonlinear Schrödinger equation in which the linear part is generated by a point interaction, H alpha. And H alpha is a family of self-adjoint operators, N2, obtained by extending a symmetric operator, the Laplacian, on Rn minus a single point. This family of self-adjoint operators is well known to those working in point interaction, but maybe not to all the audience. The dimension of the space is restricted to n equal 2 and n equal 3 because of two reasons. The one-dimensional case is well known, and I will not treat this example. And for n higher than 3, the Laplacian is essentially self-adjoint on Rn minus the point, so there is nothing to discuss because we fall in the usual case of the nonlinear Schrödinger equation. The main characteristics of this operator H alpha is that the domain, its domain changes with respect to the domain of the Laplacian, because the domain n is a singularity at the point x equal to 0, and this singularity has the same form of the fundamental solution of the Laplacian. precisely, we can represent the domain of this operator, as you can see in this line in the slide. Any element in the domain is the sum of a regular part, pi lambda. Regular means H2 in this case, and the singular part, has the same behavior at 0 at the singularity as the fundamental solution of the Laplacian. Moreover, there is a relation between the regular part and the singular part, and the coefficient, in particular, the coefficient of the singular part, Q, is proportional to the regular part at 0. G lambda is the fundamental solution of the Helmholtz operator, and lambda is any number, any positive number. Actually, the representation of the domain is independent on lambda. You cannot see this by this expression, but that's so. So the actual value of lambda positive is big lambda is the certain constant, not relevant to our analysis, but it's very important to distinguish the special superjoint extension, because the superjoint extension is parameterized by the coefficient alpha here in this constant. So we have a family, a one parameter family of superjoint extension parameterized by this parameter alpha, which is a real parameter, appearing in this constant lambda. It's not important to us which exact form has this constant. After this, after the operator domain, the operator acts in the simplest way, because the operator acts on the elements domain as the Laplacian acts on the regular part, up to the lambda more explicit and more expressed in some sense, more intuitive, is that H alpha applied to the element, domain elements psi, is minus Laplacian of psi minus Q delta distribution at the singularity 0, where Q, of course, depends on psi, because this is a linear operator. Okay, so the Q here depends on phi, and you get a linear variety in L2. It's not that phi, it's linear variety. And Q depends on phi because it is a linear operator, despite the appearance. So, given this preliminary, I will be more precise later. The nonlinear Schrödinger equation can be rewritten this way. There's a nonlinear Schrödinger equation with the delta force. Okay. Okay, this is the subject of our analysis. Some comments. As an explanation of the structure of the domain elements, we saw is the sum of a regular part and singular part. How this regular part and singular part are related to the domain elements? Okay, the Q, the coefficient of the singular part, is easily calculated as this limit. Psi over the fundamental solution of the Laplacian limit x going to 0. And there is a boundary condition at the origin, and this boundary condition at the origin, which is the second condition in the structure of the domain, is this one. You can subtract to the domain element Q times the G0, the fundamental solution of the Laplacian, take the limit for vanishing x, and you get alpha times the Q, the coefficient of the singular part. So this is the regular part, this is the singular part, and this difference is proportional to the Q. Alpha is the coefficient, the parameter fixing the special superjoint expression considered. A bit of information: the point interaction were introduced formally to treat some problems in atomic physics in the 30s by Fermi and Pyers. A rigorous definition was given by Berezin and Van Dijk as a superjoint extension of the Laplacian at the beginning of the 60s, and in other ways. Moreover, they can be considered as a limit of scaled Schrödinger operator of the standard form, minus Laplacian plus some potential. And in this sense, they describe strongly localized interactions. Notice, however, that in dimension 2 or 3, the scaling by means of which is obtained the H alpha, our operator, is not the delta scaling, but it's a weaker scaling of some special form, and some condition, an important condition about the existence of zero energy resonances on the potential V epsilon is needed to get a non-trivial loop. Potential exceptional potential in the terminology used by Piero. Okay, there is a huge literature on this subject of point interaction, and as I said before, I recall that for an higher or equal than 4, the operator S, the Laplacian on the regular infinity minus the point is essentially superjoint, and so you get triviality of the operator. Triviality means that it coincides with the Laplacian itself. Okay. Now I want to stop a moment the discussion of our equation, and I want to change. I don't know why.
Tanto potrzebne.
Okay, thank you. Okay. What? No? Okay. A digression is about this different story coming from a different field, and the story is about the singular ground state in semi-linear elliptic equations. There is a long-standing problem in elliptic equation, and not only elliptic, which is, and the question is to characterize the solution of the equation, for example, model equations such this one, minus Laplacian u plus g u to the power p, in not in Rn, but in Rn minus a point. And you can define, if you want, the positive solution vanishing at infinity of this equation as ground state if they are bounded and regular at the point x equal to 0, and singular ground state they diverge at the point x equal to 0. And of course, when g is equal to 0, everyone knows that we have the fundamental solution of the Laplacian, and singular ground states in some sense exist, and they are harmonic function in Rn minus the point 0. And
puoi tenere poco il microfono
sorry,
grazie.
sorry. If we consider the more general Schrödinger operator minus Laplacian plus p, similar results are well known. There is paper, for example, from Vasquez and Yarur in the 80s for a very large class of potential, also very similar, with similar results. In the 50s began an analysis of this problem of singular ground state existence and non-existence of singular ground states, beginning with Doug Gilbert, the famous one of Patologist, and the young James Serre, especially in the direction to establish that solutions of the equation of the quasi-linear equation, linear and quasi-linear equation in some generalities can be continuated until zero. So every singular ground state is in fact regular, is in fact a removable singularity. And the similar case, this one, was studied starting the 70s by many persons, in particular Bresis and his school. Lieb, who studied in particular the case of the Thomas Fermi theory, the P=3/2 case. Niren, and Lyon and others. So many great mathematicians. And the situation is very interesting to us because, for example, consider the case G equal to -1, the focusing case. Now, if you have a singular ground state and you have a limitation on the power p, here you have 1 minus p minus n over n minus 2, and every p for n equal to, then you get every single ground state behaves this way. The limit in the vicinity of the singularity is a certain constant. The constant is 0 when actually the singular ground state is regular. So you get a regular ground state. So singularities of focus and nonlinearities in this range of powers are all removable or weak singularity, which means singularity of the kind of singularity of the fundamental solution of the Laplacian. Moreover, each U satisfies a distribution, this kind of equation, the elliptic equation complemented with the delta surface. Over, of course, is a distribution, the whole are okay. This is not all the story because other types of singularities are possible. For example, for n higher than 3, U is a singular ground state if U is a singular ground state and this condition holds, this condition on the power p holds, the behavior of the singularity is again of algebraic type and of this type. So this is a stronger singularity. This is a stronger singularity. So we call the singularity strong singularities. In the old literature, they called this kind of singularity unvisible because they cannot be visible in distribution theory. Because the singularity is too strong to have a source. Okay. Local energy makes sense. Okay. And moreover, for Eiger and Eiger power, there are no ground state at all, no positive solutions. Okay. In the focusing case, the situation is slightly different. Okay, for high power, every singularity is removable, so it's regular. And for lower powers, you get the two behaviors simultaneously present. So the weak singularity and the high singularity, the strong singularity can be present with the same power. And in this first case, of course, you have that the singular ground state satisfied in distribution sense this equation we saw. Okay. So changing the equation, for example, taking an equation which is closer to the one we are interested in, pick the nonlinear Schrödinger equation in n minus 0 and consider the associated stationary equation, which is this one. The stationary equation obtained considering solution of special form of this form, a phase, time dependence, which is just a phase. Okay, the singular solution and the similar analogous, complete analogous classification of the one given before. In particular, the classification is essentially identical in the focusing case. So, which is the moral of this story, in my view, and which is the motivation, the further motivation to study this equation with the singularity. Isolated singularities of semi-linear elliptic equations fall in few classes, very few classes, and this is already astonishing. Some of them fit perfectly in the domain of a pointed direction, the weak singularities. And so the question is, which is the Schrödinger flow of this singularity? Which means consider a solution of the stationary, the elliptic equation with that singularity. You want to know if they evolve according to a Schrödinger flow, preserving the fact of being in the domain of the the domain of the pointed direction, and in particular they solve this equation. So it makes sense to study the well-connectedness of this equation. This is one of our motivation. This is a work, as you saw in the first slide, a work. Sorry. Maybe I'm too near to the microphone.
Non soffiarci.
Okay, this is the work done with Claudio Cacciapotti and Domenico Finco, and it's now time to consider the Cauchy product of the nonlinear Schrödinger equation of our interest, which is this one. As any nonlinear Schrödinger equation, we change the original problem in its integral version and through the doable formula. And in fact, psi is a solution of sorry, and stop it a moment because there's an issue with the microphone. In quale direzione? Vediamo. Si sente meno?
Meglio.
Meglio. Adesso si sente. Posso andare avanti?
Risonanza, proprio risonanza.
Okay, posso andare. Thank you. Sorry for the interruption. Okay, this is the nonlinear Schrödinger equation. We translate the nonlinear Schrödinger equation in the integral version, which is to the Duhamel formula. And we mean in the formula that U alpha is the unitary group associated to the superjoint operator H alpha, and F is the nonlinearity, which in our case is this the modern nonlinearity, the power nonlinearity. In shortened form, we can write the whole integral equation as in this line, and we use this shortened form. In the following, the domain of H alpha is fitted with the usual graph norm or any other norm equivalent to it. Okay. We have two results. One about the local Cauchy problem, the local well-posedness, and the other one about the global well-posedness. And the first result is given in the slide. Let us consider any psi operator domain, and there are some hypotheses on the power p. P is any power p in two dimension, and there is a strong limitation restriction on the power p instead in dimension n equal 3. P is between 1 and 3/2. With this hypothesis, we had that there is a unique solution of the integral equation in the natural phase, which is this one, because we are considering strong solutions. So continuous with values in the operator domain and differentiable in L2. There is continuous dependence on the initial data, and a blow-up alternative also in the usual way. Define the maximum resistance time, T star, and if the norm in E and in the domain H alpha of the solution psi is bounded in for T going to the maximum existence time, then T star is equal to infinity. Okay. This is the local well-posedness. There are other properties, but I limit myself to state this one. Okay. There are also global properties. The solution conserves mass and energy in the usual sense. We are considering strong solution, so this is easy. And global existence is given in this form. For n equal to, we have and one NP between 1 and 3. With the focusing equation, we have global well-posedness, and for the focusing case, we need only p higher than 1. And for n equal 3, we get the same results. The analogous condition we had for the local well-posedness, which was very restricted. In this hypothesis, the solution is lower. So you see that the condition is essentially the same as in the usual case for the two-dimensional case, but very different in the two-dimensional case. Comments. As I said before, the nonlinear Schrödinger equation is quite simple, because singularities in the one-dimensional case consist of discontinuities of the solution or its derivative and nothing more. This makes the existence theorem much easier. The only results in the nonlinear case for n equal 3 that I know are two papers in the 90s by Kaspers and Clement, considering the stationary equation by bifurcation. so different from the one treated by us. Of course, the issue is that the power nonlinearity can enhance singularities. This is the final reason of the strong limitation in the three-dimensional case. For nonlinearities of arbitrary type, there is a paper, so non-local nonlinearities. There is a paper of Alessandro Grande, Giorgiati, and Raffaele, recent paper treating also the fractional Laplacian case, so the more general dispersion. Steps of the proof are quite standard because we need some technical tools, embeddings, and Gagliardo-Nirenberg inequalities adapted to the operator H alpha and not to the standard case of the Laplacian. We need dispersing the Strickers estimates for the group associated to the separator operator H alpha. We will make use of the Cato method to get the contraction. And finally, conservation law rely on some energy bounds deduced by the Gagliardo-Nirenberg inequality in the form of the equation. Okay.
Ormai sono reattivo. Vai.
Okay, thank you. Okay, I give a sketch of the various steps. We need in the first place a scale of Hilbert spaces built on the H alpha and not on the Laplacian. And so I didn't say before, but the H alpha has a spectrum which is non-trivial, and in particular can be negative. So we have to use a translation to define the scale of Hilbert spaces in the general case. And so we define this spaces D as alpha, scale of the space built on the operator H alpha. And for this scale of Hilbert space, we can consider the useful embeddings, analogous to the solid embeddings. This is easy. Essentially, we need to consider the singularity and how the singularity interacts with being in a group. And you have a limitation of this kind for n equal 3. And so you get that the domain T alpha is embedded in the Q in this case. For n equal 3, with the limitation Q lower than 3 and any Q in n equal 2. Also, the whole scale of Hilbert spaces before can be embedded in HS with a continuous embedding with some conditions stated here in the slide. You can this is the chain of embeddings needed in the proof. I do not insist on these technical details, and by interpolation you can obtain also Gagliardo-Nirenberg inequalities in the fog domain. And the Gagliardo-Nirenberg inequality again have a usual form in the case n equal 2 and are restricted in parameters when n equal to with the usual definition of the critical response. in particular, the variable quality will be needed to get the control of the energy, of course, because we're going to control the nonlinearity. Nonlinearity is essentially equinorm, and so you want to have the control of this curves. Okay. Moreover, you need stricter estimates that are needed in the Cato strategy, and there is an analysis of the dispersive properties of the operator, the unitary group associated to H alpha due to the D'Antonio, Michelangelo Scandone, and Yajima, and then Cornea, Michelangelo Yajima. And there is also a previous paper due to Piero D'Ancona, De Felice, and Alessandro Teta, and dating 2006. And those a paper by Iannoli and Raffaele Scandone, a more recent paper, Iannoli and Scandone. Based on these results, one can show in a standard way figure estimates of this form. There is nothing especially new in these estimates, but they are useful, and so they are stated here. Okay. The sketch makes use of the sketch of the proof. Okay, we want to use the Cato strategy. The Cato strategy makes use of some auxiliary spaces. And you see, for example, this is the first auxiliary space. You see that the natural space where one would like to work in is an infinity, but we need a restriction to a smaller space, which is given by this space LR p plus 1, and in cascade you have some other spaces again with a restriction, or when you need the dual enlargement. The main point is that the unitary group U alpha, or the integral of the unitary group, which is called gamma alpha, the operator needed in the inhomogeneous assessments, are bounded operator in this space. Okay. After this, the proof is along the known lines, and essentially amounts to obtain a contraction in a certain metric space, the complete metric space, which is this space A, E, which is a certain ball in the space theta given before. With the condition that at time 0 they be coincide with the initial datum chosen for your push okay. Actually, you have the contraction you want to have, and so for sufficiently small t, the operator phi, so the operator appearing in the integral form of the equation, is a contraction, and you get the local well-positiveness. Then you have some technical step allow you to show that you have the regularity, the further regularity you need to have the strong solution, but this is the main step. Just a remark, it does not appear from the sketch, but the uniqueness is unconditional, because the restriction, the restricted space, means that the original contraction gives you uniqueness in the restricted space. So you to have the uniqueness in the complete form in the strong sense, you need to show that the restriction is not needed. And the consequence is that you have the uniqueness that you want, and the more you have the solution is in the restricted space. So this is a bonus information of the theory. This is a typical situation appearing in the Caton method. The global well posedness is completely standard because you make use of the Gallardo-Nirenberg inequalities. The strong solution allows you to get easily conservation of mass and energy. Then the Gallardo-Nirenberg inequality allow you to get the bound on the linearity, on the nonlinearity in terms of the quantity that are under control. And you get, as already said, that for example, for G equal to 1, so the focus in case an immediate control of the energy, which is control of the solution in the energy norm, and for G equal to -1, the control is submitted to some condition, which are the one you can expect. For P, for n equal 3, we have the same condition giving the local well posedness, because the condition is so restricted that guarantees also the local well posedness. Is the situation with the n equal 3 case. Okay, after this brief sketch, some comments. Sorry. The constraint in the n equal 3 is essentially due to this condition. The singularity has to belong to it. So in some sense is a restriction due to the need to force an Hilbert space theory. My expectation is that to work out of the Hilbert space setting is do better. The Hilbert space setting is not, we are not obliged to use an Hilbert space formulation, of course, but in some sense, pointed direction are born in the truth, and so this inertia is the reason for this setting, functional setting. The proof and the result are insensitive to the value of formula of the self-adjoint parameter alpha, extension parameter alpha. For other comments are okay. I think that the most interesting case in the end is the n equal to case, because there is more room for the search for solution. Everything is according to the usual expectation, and I think that the n equal 3 case is somewhat pathological. But this is an opinion. And conclusions, and I go to the conclusions. Okay, we have a well posedness local and global for strong solution of this abstract nonlinear Schrödinger equation. And my point, apart from the result, one more result of well posedness about well posedness in abstract Schrödinger equation is that there is some coincidence of behavior of this theory with the behavior of quick singularities of for semi-linear elliptic operators. So reference linear elliptic equations. And I think this is interesting because it opens some perspectives and direction of analysis. Perspectives, there is, we can, without effort, to generalize the whole concept to the case of the energy domain, the fog domain, again using the Kato strategy, it's essentially identical. We did the result in the for strong solution because we had in mind applications. Stationary standing waves, bifurcation theory, and so. And for that, some more variety is useful. There is the possibility to study the evolution in the critical case, and maybe in particular maybe interesting the n equal to case. Of course, existence and stability of stationary solution is much to do, and there is a theory of point iteration in NP, and I think that this could be useful to generalize the result and to make a little better the result in the n equal to case. An open question. Is there a convenient setting for the evolution of strong singularities? As we have seen, there are two kinds of singularities. The weak that are described by this family of self-adjoint operator, well described, and the strong. Where to locate the strong singularity and how they could evolve, for example, according to the Schrödinger theory. This I have no idea about the possible setting to when to construct this problem. Okay, I think I can stop here.
Thank you very much for the interesting talk. And are there some questions, remarks?
Probably I missed something. If I'm not wrong, your local Cauchy theory is in the domain of the operator. And you want to globalize by controlling the square root of the domain. How do you do that?
How?
You control something weaker than the norm of the domain. So do you globalize?
I control okay, but the question is why I use why I consider the I control in the maybe I wrote something wrong, but I control the domain, the norm of the operator domain. Maybe I wrote the wrong.
But not just by energy, not the easy one, it is something modified.
Yeah.
Some other questions or observations?
Concerning the last point on considering the strong singularities in some setting not related to one equation. Okay, maybe there is no way to consider a correspondent operator setting maybe the distributional interpretation of the point interaction can be extended. You can get a more general process of removing singularity, which gives you, I don't know if
Okay.
something is possible.
You mean
Yes, instead of the interpretation of an operator, the interpretation of removing some distribution, which is not a delta, but maybe something more general class.
actually the singularity that singularity has no distributional interpretation. And the issue is that you get the same equation. You are not able to recognize the presence of a singularity extending the equation everywhere because there is no distribution representing that singularity.
Okay.
So the question, I know the answer to the question, and I wonder which could be. Maybe
If I understand, if I remember, you have all the singularities related to the delta, or the other one are too strong that are not have a distributional meaning. There's nothing in the middle. Okay.
nothing in the middle. The astonishing fact that you have the bottom, or that, or the other. No other kind of singularity can be present in that nonlinear operator.
Okay, so also for distribution, the only way you can interpret like the volume distribution is the case of the delta.
The only compilation of the equation as a distributional equation is the one related to the weak singularity.
And just another, another remark. I mean, okay, I understand that in the case of the Taylor domain, there is a bit more technical step and lead, but in L2, I mean, what you have is enough, no, for the local.
I think in L2, I think it's easy.
Yeah.
I think there is no problem to get the localization still in each one in the form domain and operator domain. The technique is essentially the same. It's done in the original paper of Capo 1986. He did both the case. So I think, as I said, we did the strong solution. We studied the strong solution having in mind applications, but I think I can understand it.
Some other questions, remarks, please, Alessandro.
Isn't it possible to extend the analysis to the case of endpoint interactions?
I think yes, but for laziness, due to laziness, we avoid to extend to endpoint interaction. But one can extend to the endpoint case. So the singularities are fixed. By the way, there is a theory for n or infinite singularities, also for the mentioned case of the elliptic equations with the isolated singularity. There is also a more fine analysis for quite more general zero measure singularity. No, I think so.
You related to this question, in the general case of n point interaction, some exceptional case you can have zero energy resonance, no? So I think you may want to avoid that case.
Maybe you have some okay. You mean you could have difficulties with the sticker estimates?
Yes.
Okay. Probably you need some conditions on the okay. I agree, but I didn't.
I mean, it's the only way using
I think there is a really nice point to continue the discussion during the coffee break.
Maybe some
Yes.
Or
Some questions.
No. Okay.
Okay. Seems that we can be prepared for the coffee break, but before let's thank the speaker again.